If you've ever had your application just grind to a halt, and you've seen that cryptic deadlock error pop up, well, you've met the challenge we're going to tackle today. We are going to demystify MySQL transactions and show you exactly how to handle this super common, but yeah, very frustrating problem.
So let's start with a pretty simple question. Just imagine an e-commerce flash sale. You and somebody else are both trying to buy the very last item in stock at the exact same millisecond. What's supposed to happen? I mean, who gets it? And more importantly, how do we stop the whole system from just crashing under the pressure?
Well, in a poorly managed system, it would lead to total chaos. You'd get corrupted data, overselling, a real mess. But fortunately, your database isn't a free-for-all. It has a built-in guardian, a set of rules and mechanisms designed specifically to prevent this kind of disaster. And today, we're going to get to know this guardian very, very well.
And this brings us right to the heart of the matter, the concurrency challenge. Databases, by their very nature, are shared resources. You've got tons of people, tons of applications, all trying to read and write data at the same time. To keep things in order and make sure your data is trustworthy, you absolutely need a system of control.
That system of control is built around this idea of a transaction. You can think of it like a promise. Let's say you're transferring money. You're really doing two things, right? You're taking money from one account and adding it to another. A transaction wraps both of those steps into one single unit of work. And here's the key, it's an all-or-nothing deal. Either both steps happen successfully or neither of them do. There is no in-between.
All of this is possible because our guardian follows a really strict code of conduct. We call it ACID. It stands for atomicity. That's the all-or-nothing part. Consistency, making sure the data is always valid. Isolation, so transactions don't trip over each other. And durability. Once data is saved, it stays saved, no matter what. This code is the absolute bedrock of data integrity.
So, how does our guardian actually enforce these ACID rules, especially isolation? I mean, how does it stop all those transactions from stepping on each other's toes? The answer lies in something pretty powerful, locking.
To make sure transactions stay isolated, MySQL uses locks, and they come in two main flavors. First, you've got a shared lock, which is for reading. You can think of it like a bunch of people reading the same book in a library. No problem there, right? But then you have an exclusive lock. This is for writing. If you want to make notes in that book, you have to be the only one holding it. This stops anyone else from reading or writing until you are completely done.
And you know, modern database engines like MySQL's NODB are incredibly smart about this. Instead of locking down the entire library, the whole database table, it just locks the specific book, or even just the specific page you're working on. This is called row-level locking, and it's what allows tons of users to work in the same table at the same time without constantly waiting for each other. It's a huge deal for performance.
But, and you knew there was a but coming, here's the twist. These locks, the very tools that are designed to protect us, can sometimes turn on each other and create a whole new problem. This is what happens when locks collide, and this is when we get a deadlock.
So what is a deadlock? It's basically a digital standoff, a classic catch-22. It happens when two or more transactions get completely stuck because each one is waiting for a lock that the other one is holding. They're trapped in this circular wait, and neither one can move forward.
Okay, let's watch this happen in slow motion. Here comes transaction 1. It starts up, and its first move is to update account 1. So, boom, it gets an exclusive lock on that row. Simple enough. But its next step is to update account 2, and this is where it hits a wall. It has to wait. Why?
Because at the exact same moment, transaction 2 started. Its first step was to update account 2, so it locked that row. And its next step, you guessed it, it needs to update account 1. And now we have a serious problem.
And there it is, the gridlock. Transaction 1 is account 1 locked and needs account 2. Transaction 2 has account 2 locked and needs account 1. Neither can proceed. Now, if left to their own devices, they'd wait forever, but MySQL is way too smart for that. It has a deadlock detection system. It sees this circular wait, declares one of the transactions the victim, and rolls it back. That frees up the lock so the other one can finally finish.
So, deadlocks happen. It's a fact of life in busy databases. But the good news is, we are not helpless here. We can actually design our systems to avoid them most of the time. So let's open up the Deadlock Prevention Playbook.
Okay, this is your core checklist. First, and this is a big one, enforce a strict order. If all your code always updates account 1 before account 2, That deadlock scenario we just saw becomes impossible. Next, keep your transactions short and sweet. Get in, do your work, commit, and get out. Release those locks. Use your indexes properly to avoid locking huge chunks of a table. Use the lowest practical isolation level you can get away with. And critically, never ever hold a transaction open while you're waiting for a user to click a button.
But let's be realistic. Even with the best prevention strategies in the world, in a really complex, high-traffic system, deadlocks can still happen. So the next step isn't just about prevention, it's about building resilient code that knows what to do when a deadlock eventually shows up.
The solution is this really powerful pattern called retry logic. Now, the code might look a little complicated, but the idea is actually super simple. You write your application to catch that specific deadlock error. Instead of crashing, it just pauses for a split second and tries the whole transaction again. By then, the other transaction has usually finished, the coast is clear, and the second attempt just sails right through. So let's pull this all together. It's really a multi-layered strategy. You start with smart design. That means using indexes and having a consistent access order for your data. Then you write resilient code with short transactions and that all-important retry logic. You configure the right isolation level for what you need, and you monitor everything to catch issues before they become major problems. It's all about being proactive at every single level. And if there's one number you take away from this, let it be this one, 1213. When MySQL detects a deadlock and picks a victim, it doesn't just fail silently. It sends back error code 1213. This is the exact signal your application code needs to listen for to trigger that retry logic. You see 123? You know what to do. Time to try again.
And that brings us to the most important takeaway of all. A deadlock isn't a bug, it's not a failure. It's actually a sign that the system is working, that the locks are successfully protecting your data from getting corrupted. So your goal isn't the impossible task of eliminating them completely, but the much more practical one of building a system that can handle them gracefully when they happen.
And that's our deep dive. You now have the playbook for understanding, preventing, and handling deadlocks. So the final question is really for you. Think about the applications and the systems you work on. Where is the potential for the next gridlock? And how can you use these strategies to make it more resilient?